Hello everyone, my name is Jasmine Aloor. This summer I worked on multi-modal socially aware imitation learning for general aviation as a part of Robotics Institute Summer Scholar Program. My mentors are Jay Patrikar and Dr. Sebastian Scherer from the Air Lab, Carnegie Mellon University. The future of aviation will see a massive increase in low-altitude aircraft operations that fall under general aviation. An increase in the number of flight hours result in increased conflict and conflict resolutions. In the absence of a centralized traffic control tower in the vicinity of airports, pilots are expected to follow the FAA guidelines, be socially compliant, maintain separation by taking flexible actions. With each aircraft having a specific goal and requiring to maintain safety, guiding general aviation aircraft is a social navigation problem. Two main directions have emerged in recent research. Reinforcement learning methods have a shortcoming when the reward function structure is not well defined. Training in the real world is difficult and expensive, and using a multi-agent simulator presents the issue of accurately modeling human-like piloting behavior, which leads us to the initial problem. On the other hand, learning from expert human demonstrations using inverse reinforcement learning or imitation learning can attempt to provide a more natural, human-like motion, and it's a popular research direction. This work uses the recently released TrajAir Dataset, which is collected at the Pittsburgh Butler Regional Airport. Here, we observe that the airport traffic pattern, a rectangular shaped pattern, ensuring air traffic is flown into and out of an airport safely and in an orderly manner. The dataset trajectories are smoothed using B-spline approximate representation of degree 2. We consider a fixed-wing aircraft flying in three-dimensional Euclidean space to calculate a set of trajectories in the inertial frame. We choose three broad categories of motion: steady level flight, steady climb and descent, and coordinated turns. We vary the velocity, rates of climb, and banked angles over the chosen time horizon. In this work, we use a form of imitation learning known as behavior cloning that learns a policy from expert demonstration, taking as input the past trajectories of all agents along with the weather context to predict the next action. The model uses a temporal convolutional network to process the sequential trajectory data. We break the trajectories in a scene into sequences of fixed length. We encode the trajectories and concatenate them to output a single motion primitive at each iteration. The selected action from the motion primitive library is sent to the agent. The trajectory data and the environmental context vector for each agent is collected to close the loop. Here we show simulation results of an action predicted. Actions are input to the X-plane visualizer. On the top right, we see the track trajectory. On the bottom, we see the dataset trajectory and the predicted actions. Here the aircraft is commanded to take a right turn. We also show a failure case. The green arrow shows the locations where the actions were wrongly predicted opposite to the direction of motion of the agent. We thus see behavior cloning requiring a large number of demonstrations, and it deviates when encountered with out-of-distribution states. We use three evaluation metrics: average displacement error and final displacement error for the trajectories, and cross-entropy loss for the selection of motion primitives. Our next step is to collect feedback interactively and provide the expert full control to intervene. As the expert actions are aggregated, we expect the algorithm trains a new policy with significant improvement. We would use the interventions from supervisor to bring back to safety, update the algorithm, and learn. As I conclude, I would like to thank my mentors Jay Patrikar and Dr. Sebastian Scherer for guidance and mentorship throughout the summer. I would like to specially thank Ms. Rachel Burson and Dr. John Dolan for the support and encouragement throughout the program. This work was supported by the Air Lab at the Robotics Institute, Carnegie Mellon University, and I'd like to thank everyone who made this research experience possible. Thank you.